So I would like to introduce our next speakers. We have Stuart Hode and Hugh Breslin from Microchip. Sorry. Thank you.
So thanks very much, everyone, for joining us. We're going to talk a little bit about some work that we've been doing as part of our Mi5 ecosystem. So though Palmer said there was 11 software talks, this one's not really a software talk, but I kind of sneaked in there, so they gave me a longer slot. So don't be surprised when there's not too much to talk about software here, though we will talk about compliance, and that's a pretty important part for ensuring tool compatibility. So I'm going to give you a brief introduction to what Mi5 actually is, so that you just got a bit of background as to the context of this. And I'll talk a bit about why we need verification and compliance as part of the work we've been doing. Hugh is then going to talk a little bit about some work that he's been leading with regard to cross-platform compliance and verification on various different platforms that we work on. Then I'm going to introduce some work that we started quite a long time ago in the early days of our involvement in RISC-V, but this particular project that we've been working on was a good time to apply this to some real problems we've had. So I'm going to introduce some work we've been doing on formal verification of RTL. So here's the quick marketing slide. So to introduce what Mi5 actually is. So Mi5 is something we created to sort of bring together an ecosystem for supporting the CPUs, the RISC-V CPUs that we build for our FPGA platforms primarily. So it encompasses everything really that you need to use RISC-V cores, including operating systems, design tools, boards, example solutions, and of course the CPUs themselves. And here, this talk is primarily going to be about the CPUs that we've been packaging up as part of our Mi5 delivery. So why we're not a processor company per se, or at least when we started this work as Microsemi, we weren't a processor company. So why do we need a compliance and verification suite? So ideally, we'd like to be able to take and use open source cores, and Microsemi, Microchip make a lot more devices than just FPGAs, including some very large devices and very complicated. And Rick talked yesterday about going to see your boss and presenting him with this great idea to use RISC-V, and then saying, yeah, it will be fine. And some of these ASIC developments that we do are extremely expensive, and they have a lot of embedded processors in. And we would like to be able to use open source cores, but they have to have a known quality. So when we buy cores from commercial vendors, we can understand their verification processes, we can understand the design quality, and we have a pretty good idea of how well they're going to work. And we can work with them to address anything we need to on that. That's not necessarily the case when we use open source cores. So therefore, we have to do something different to ensure that same level of quality, because we do require that same level of quality in ASIC design. We also require very high quality in the cores that we deliver as part of our FPGA platform as well, because our customers are picking these cores up and using them for real applications, so they must work. So we'd also like all cores to be compliant, of course. So I lead a co-chair of the compliance working group for RISC-V. So this is a pretty good opportunity to take some of the work that the compliance working group have been working really hard on. So thanks to people like Codesip and Imperis, who've donated a lot of time and effort into that work. So we worked with Imperis to target the compliance work that the working group have been doing at the cores that we are building. So one of the things that we've been talking about in the compliance group is the requirement to test the compliance suite on various different platforms. And we have an opportunity to do that here. So Hugh's going to talk about the work we did there. We also, as I say, in our early days in RISC-V, looked at the deficiencies in verification in RISC-V. And we're thinking about how to address that. Because realistically, it's very difficult to achieve the verification quality of someone like ARM, because they have a lot of history in in building processor cores, they built up a huge amount of verification IP, and they have a huge amount of resources to apply to the verification problem. So how do we kind of apply modern techniques like formal methods to try and achieve a similar verification quality in a much shorter time on RISC-V? So I'm going to talk a little bit about that and how that fits into what we call a super compliance, if you like. So at the moment, the compliance suite doesn't have any tests for the privilege architecture. So here's a call to action for everyone. If you want to spend some time helping us with compliance, we need to figure out how to build a compliance suite for the privilege architecture. But in the short term, we needed something else for our Mi5 cores. So we decided that formal methods would be the approach we use there. So all of our compliance on the privileged architecture part of the cores is done with formal techniques. So I'm going to hand over to you here.
Thank you, Stuart. Can everyone hear me? So my name is Hugh Breslin. I'm an embedded Linux engineer with Microchip. So I'm going to be talking to you about the work that we did in compliance and verification and the kind of software side of that. So there are three main things that we ended up looking at for compliance and verification. So that was, one, we made this thing that we called RISC-V VIP, which will allow us to run compliance tests, torture tests, and it'll do that in a simulation environment. Then we have the Mi5 compliance suite, which will run the compliance tests, which were developed by Impress and CodeSIP, which we wouldn't be able to do ourselves. And that'll run for us in a hardware, emulation or simulation environment. And then we also have our benchmarks, and we've got a new one to add on from talks that happened earlier on. And we can have a look at MBench as well. So if we have a look at the RISC-V VIP that we put together, it uses an AHB interface, and on the left-hand side here I have our Mi5, which is an RV32 IMA core with an L1 cache and AHB interface, and that's connected up to our VIP. And what it'll do is it can pass selections of hex files into the core, run the tests, and then compare the resulting memory with a reference memory signature. And we also have our VIP set up so it can be used either with, we have a cached and uncached interface on this core, but we have cores that we could have cores that have or just a single interface, and we can use it on that. So when we're looking at the VIP, then it can be configured to run the compliance tests or torture tests. The compliance tests were the tests from the RISC-V compliance GitHub developed by CodeSIP and Impress, and we currently have support for the I, M, and C extensions in that. And then in terms of torture tests, they were generated by scripts provided by Clifford Wolf. And once again, we have support for IM and C extensions, and we can generate 1,000 tests for 8 different configurations. So that gives us 8,000 tests that we can actually run. And from that, then we can generate some coverage to see what instructions we were testing, how often we were testing them, and then as well, if we were hitting all of the registers and so on. And then in terms of the RISC-V compliance, we aren't really running it on the core, we're trying to run on our SoC. So that meant then that we had to figure out a way of getting the information into the core and then getting it back out again. And we wanted to try and do it with our IDE. So that meant then we ended up having to change the test slightly, where we added in and made the test functions, and then we could call the functions from a main. And that meant then we could either say, oh, we just want to run the add test, build a hex file to test that, or we could build a hex file to test all of the I extension instructions. And then to print out our results, we created a UART buffer using our linker script, and then just changed where the results were being saved to and saved them to our UART buffer. And that meant then at the end of the test, we can either flush the UART buffer, or if we were running in simulation where we don't really need UART to print out results, we can just watch the memory writes that were coming out. So if we have a look at how we actually did that, here's an example of this running on hardware. So I'm printing my results out over UART, and that's on COM37. So I've built my program already, which is going to test the I extension, and I can launch a debug session, which will connect GDB to my core. And then in my main, then it means I can initialize my core. So if you needed to set up any peripherals beforehand, like your UART, and I initialize our PLIC as an example, but that'll then get me down to my tests. My signature results will be spit out into my terminal, and then I can just copy and paste my results from my terminal into a text file and use a bit of Python to do a comparison of my UART output versus the golden reference signatures that we already have. So when I do that, then it can do just a very handy compare for me, and then tell me whether I passed or failed the compliance tests. So give it a second, and I'll just hop over to my console, and you can see out of all the tests, I ran 53 tests, and I passed all of them. So that's very helpful, and it's very useful to be able to do it on hardware, but then we can also run it in Renode, which is our emulation platform. And what's quite helpful there, or it's the Renode emulation platform from Antmicro, it's integrated into our IDE. So I can run, without having to change my program at all or reconfigure anything, I can start a debug session, run Renode, and what's very handy is as well, I can get my UART output to log directly to a file in Renode and get my Python to run directly after that. So it's going to just spit out all of my test results for me once again, and then if I just let it run through and then stop my program, my Python will start up for me automatically because I was able to add it all into a launch group. And then once Renode has saved my UART output, once again, I've passed 53 out of 53 tests. And then finally, if I just wanted to have a look at this in a simulation environment, what we did was we added in a define, so basically all this says is I don't want to use UART. And that means then it runs a lot faster, there's a lot less initialization to do, I don't have any printfs in there. So then I can just use, Libro is our IDE, or for FPGA development, I can initialize a memory in it. So I've put in, I'm actually just running the I tests in this, put in my hex file to initialize a memory, and then run a simulation to actually get the results. And what's handy is, because I've defined my store location, I can see all of my writes with my signature data coming out on a different memory interface, which means then that I don't have to try and figure out when it's saving signature data and when it's not. So if I add all of the signals for my top-level design and then run my simulation, you'll be able to see, once it's initialized my core, it'll start running the tests. So if you just give it a second, my initialized memory is on on slave 8, and then my signature results are going to come out on slave 6. So just going to let that run through, and slave 6 is the one on the top. And then after it's done all of my initialization, it started printing out signature data, which is just stores to those memory addresses. So that's kind of where we've been, or that's what we've been working on. That's how we've managed to get it to work, and it's gone quite well. And I have to say, it's been a brilliant help having the tests there from Impress and Codesip, because we wouldn't have had time to actually go and develop our own tests. So that is the bulk of what I have to get through. I'll pass it back over to Stuart to talk about his formal work.
I'm going to kind of make a sweeping assertion here that simulation isn't sufficient for processor design. So no matter how much effort you put into it, you can't possibly cover everything in a test and check based approach. So processors, even in their relatively simple form, are fairly complex. We have lots of corner cases in processors, even simple ones. So things like forwarding paths, for example, or exception handlers and things like that, introduce corner cases into the process design. And these are things we have to execute in simulation. So therefore, like I said, several years ago, we started a program to think about how we could possibly formally verify CPUs. And since then, we've seen work from ARM and from Clifford on formally verifying processors. So one of the problems with simulation, as you may well know, and even emulation as well, emulation is really just performing simulation really fast, or putting in FPGAs, is are we actually really covering everything we need to? And how do we even know that we're covering everything we need to? So I put here, formal methods are good for processor verification. In fact, I'd say they're ideal for processor verification. They're very good. And here we're talking about, by the way, about model checking of RTL here. They're very good for finding corner cases very quickly. So one of the challenges when we perform formal verification, so we use formal verification generally in RTL design, but one of the challenges typically in the general case is specifying the design. So in formal verification, we write properties about the design and we prove whether they hold or don't hold based on a certain set of conditions which are set by constraints on the design. And that can be pretty challenging to do in the general case. Fortunately, for a processor, it's actually really easy because a processor has fairly limited interfaces. They're usually well-defined, like AXI or TileLink. And in our case, the specification of what it's actually supposed to do is very clearly defined in the ISA itself. And even better, from RISC-V's perspective, is there's a whole working group and a whole bunch of people who are formalizing that ISA. So that makes our life much better because someone's already done the formalization. So now we can create properties and we can prove them. One of the other advantages that we see with using formal methods, so typically when we're doing process design, we may be somewhat like pessimistic about certain things like buffer sizes or things like that, queue lengths and things. But if we know for sure that we can absolutely prove whether something works or not, we can be a lot more aggressive in those techniques. And we can in fact use the formal tools as well to help us understand what the limits of things are. So we can say, can all the buffer locations actually be used? And if they can't, we can make our buffers smaller, or we can perform other optimizations in the design. As I say, one of the questions we have in the compliance working group is where does compliance end and where does verification begin? So what are the permutations that we should actually really test under compliance? So in formal methods, we can leave things undefined, and therefore we can cover the entirety of the space. So therefore we can perform a form of super compliance. So we've been thinking a bit about how would we use the formal tools to actually aid us with compliance as well as full verification. Oh, went the wrong way there. Sorry, I made the text a little bit small here, so apologies for that, but I'll give you the kind of general overview. The color's also gone a bit wrong, so I'll have to do some pointing here. So essentially, the technique we're using to formally verify processes is similar to the one in the ARM ISA formal and RISC-V formal as well from Clifford. But there's some significant differences in the approach we've taken because we're not necessarily assuming that the CPUs that we're integrating are our own CPUs, or we have any way of understanding where certain architectural state is. So, for example, ISA formal requires a bus with the GPR state, but we're not assuming that we can actually even get hold of that. So we're looking at a slightly different approach to use that. So on this diagram on the right, these are the three main parts of our formal setup. So we've got the processor itself, which is this blue box here. Then we have a formal model. So what we ideally want to do is compare that the processor implementation is equivalent to this formal implementation, formal model of the processor. So this formal model is written in System Verilog, and I'm going to talk a little bit more about some of the details there. And then we have this abstraction layer. And the whole purpose of this is really so that we can test with different CPUs without changing the way the formal model looks and works. And we can abstract all the implementation details, what signals what, in this abstraction layer. Additionally, we have this thing which we call a execution path buffer. We don't actually use that in the current cores that we're using because we can get direct access to the program counter. So we don't use that. So one of the cores we're testing is a modified version of Clifford's Pico core. So we added in debug and the privileged architecture to that core. So those are the things we're primarily testing there. And the other one is a ground-up CPU. It's an internal one that we used as a test vehicle for this. So the key thing that we're trying to check is we're trying to check that these designs are equivalent by comparing the program counter. So we expect the execution to be the same. And we can show that any possible failure can propagate to the program counter. And if the program flow can deviate, therefore there's something wrong. In fact, things like GPR failures, they can all propagate via things like jump and link to a different program flow. So I'm going to talk a little bit about the model. So known knowns and known unknowns. We probably have unknown unknowns in there as well, but we don't know about those, as I think Donald Rumsfeld famously told us. So in the RISC-V architecture, there's a bunch of things that are undefined. And some of those are undefined out of reset. In fact, most things are undefined out of reset in the RISC-V architecture. There's only a few things that the architecture actually specifies that have to be reset to a known value. So therefore, when our model starts up, it has a whole bunch of architectural state that's in an unknown value. And there are some things in the implementation that are undefined or have implementation-specific descriptions. So how do we check equivalence with such a thing? So if we have an implementation, how do we know that the architectural state is the same? So one approach we could take is we could attempt to initialize the architectural state. So we could do that. So if we were in say, a software-based compliance test, we do that because our framework goes through and initializes all the state. It initializes to a known value. But that's not great from the model checking perspective because that means that we have to execute a whole bunch of stuff. The formal tools do actually allow us to poke in them and initialize architectural state, but we didn't really want to do that, and we didn't want to have to go to the overhead of trying to understand where that architectural state actually lives in an implementation of a core. Remember I said they're not necessarily our cores, and in some implementations, not the ones we're currently looking at, that may be extremely hard to do. So we try to avoid doing that. So we're looking for a different approach. So I'm going to talk faster here. So we created a system Verilog model that allows us to handle these unknown states, if you like. And by doing that, it means we don't need to apply initializations and we don't need to apply constraints to design, which may over-constrain design. We may miss bugs by doing that. And it also means we can do a lot of abstraction work, which allows the model checker to actually make deeper proofs. So we're still mostly doing bounded proofs with this thing, but we did a bunch of, we're doing a lot of work with Cadence to show what that exactly covers in our formal model, to show that that's sufficient. So a few more details about our known value logic model. So it's a 4-state logic model. So in the model checker, typically things are 2 states, they're 1 or 0. So we have to explicitly create a data type to allow us to tell us whether we know the value or whether it's unknown. And then we have to build a logic model, all the arithmetic functions as well, to allow these to be actually propagated. So this took quite a lot of work, and it's not entirely optimal. So this is still an ongoing work that we're doing. And so here's an example to show how this actually works. So in this case here, imagine we have the case where we have a CSR that's implemented, and we did actually have this case. So this was a real one, but it doesn't have the right access privilege. So how does our formal tool detect that and propagate that to the program counter? So it's actually the second instruction, which is kind of the important here. So we try and do this CSR operation to the offending CSR, and if the implementation incorrectly allows us to access that, it happily carries on with its sequential execution. So its program counter increments to the next instruction, whereas in fact, really, it should be jumping to the exception vector. So we get that deviation in the program counter, and we can detect that, and we know we go in and debug it. So the important thing is actually this first instruction here as well, because remember, in our known logic model, we have to know that we know the value, because we don't check unknown values. Therefore, the formal tool will automatically insert this instruction here first to initialize the empty vec register. But we don't actually have to tell the tool that. It knows that in order to propagate a known value, it has to go and do something to initialize it. So we don't have to bother with building states. It's defined in the architecture. And what we found with this, so it kind of depends on the core. So on the Pico core, where we were adding privileged architecture, most of the failures we see are in the CSR. Clifford would be very happy to know that we didn't find any further errors in the stuff that he already built and tested. So his formal work obviously worked pretty well. But it was in primarily in CSR accesses and privileges where we were finding issues there. And then in the ground up one, as we'd expect, where it's much more of a design bring up tool, it's failures in the pipeline primarily that we're debugging. But it shows that this approach can actually be widely applied to various stages in the design process. So to wrap things up, because I think I'm just about out of time, I missed the card holding up thing. I was not concentrating. So in summary, so we built a suite of tests and to combine both more traditional verification techniques and simulation and the compliance work with some new work that we're doing in formal to provide us a lot of confidence in the quality of the cores that we're delivering and we're using in our ASIC products too. So, excuse me. And I just want to sort of wrap this up by saying that is the work currently on there? So this is our This is our GitHub repository for our FPGA work. So most of our Mi5 work is open source. And the plan is as well that eventually when we get through the scrubbing and approvals, the formal work will be on there as well. Thank you.
Thank you. We can do one question. One question all the way in the back. I can't throw it that far.
Hello.
Hi.
I would like to ask maybe if I misunderstood some part, but you mentioned that it's very easy to constrain processors and you can formally verify it, but assuming you have a little bit complex processor like a dual issue, which has branch predictors, branch target buffers, and it can compensate load delays with more ALUs in the pipeline. So at some point, you really need to align the stars to find a bug in the pipeline, for example.
Right.
How do you approach this? I mean, how do you?
Well, that's why we're proposing using formal methods to do that, because formal methods, the tools are trying to find a failure, as opposed to it's not a test and check type approach. So can a property ever be violated? I'm not sure if that answers your question. We can take it off. We can talk more offline.
All right. Thank you, Stuart and Hugh.
Thank you.
All right. Our next speaker is Richard Berry. He is the founder of Free Art.